Okay, so like in the last video, we basically discussed the Airy stress function and how the Airy stress function basically helps us to basically get the solution for like stress and strain. So like once we find the Airy stress function that satisfies the Laplace and also the boundary conditions for the problem, then we have basically every stress and strain value for every point for that problem. So like now that we have done that for Cartesian, we can now also analyze the Airy stress function in polar coordinates. So for polar coordinates, we can basically start that we have the gradient of sigma is equal, plus f is equal to 0. So like where we have the gradient components as this, like this were derived, like also this is also in this. So like we gradient of sigma in the r direction and in the theta direction. So like for the Airy stress function, we can basically define, like since for Airy stress function Cartesian, we defined it as sigma x is equals to del square phi upon del y square. So like we can basically derive the Airy stress function in the r coordinate form as this. Like once we have this Airy stress function in terms of phi of r comma theta, then we can basically construct this sigma r and sigma theta as this. We can write the radius function in terms of this. So like in the r coordinate, it's simple, but to get the phi coordinate, you have to divide by 1 by r square 2 because of the curvilinear constants. And like we can see that when we plug this sigma r values into this equation, then it automatically gives us 0. So like basically these are found by basically like when we put this in 0, it automatically satisfies the conservation of mass equation. So like we have the sigma r and sigma theta components in terms of this, and we also have the tau xy components, which is like basically this, and it's also very simple. So we know that the Laplace in polar coordinates. So like now that we have stress in terms of the Airy stress function, we can basically find each and every part of this. So like we know the Airy stress function should always satisfy this raised to 4 of 5 is equals to 0. So like if we solve it and get this Airy stress function, then we can find the radial and theta components of the stress and the stress, and then from the stress we can obviously find the strain. So basically, we know that the Laplace equation in polar coordinates, the Laplacian is in polar coordinates is basically this entire things, and we know that the for plane stress or plane strain problem, we have to satisfy the series stress function of this. So basically, we have to apply this Laplace operator twice, the Laplace of phi. So like obviously since it's a differential equation, we can basically find the solution. So like I mean it's like basically it's a Cauchy's formula. Like when we write this equation, we assume that there is an axisymmetric state of stress. So like there is no theta dependence. So like all by del theta terms would go to 0. So like we have only one variable then, like our state stress would be depending on only one variable, that is r. So like when we write the Laplace equation, del by del theta terms would be 0. So a general solution in terms of all the radial terms is this. So like we have sigma r is equal to a1 by r square plus 2a2 plus 2a3 ln r and plus 2a3, and this is also like same. So like we have basically that this is the basically solution which we have for phi using this. And then once we differentiate the phi terms, we basically get the sigma r, sigma theta, and sigma y values. So like we have the solution for this gradient square of phi is equal to 0, and then from there we have, since we have the solution, we just basically wrote this in terms of sigma r and sigma theta and so on. So that's basically this. So like now that we have this, like we can basically apply some boundary conditions that we cannot have ln terms in our this, because like ln terms would blow up at 0 and infinity. So like we would not get a solution at r equals to 0. So basically a3 terms are all 0. So and also there's another condition that u of 2 pi plus theta should be equals to u of theta basically. So like if these two conditions are put, then like in this case we have a3 is equals to 0. So like after putting a3 equals to 0, we can just basically club the other constant. So like basically our sigma r and sigma theta are basically in terms of this. So like if we have a axisymmetric problem, that is like it's not dependent on theta, like it's basically kind of a circular problem, it's not dependent on theta, it's same for every theta. So for that case, we have our sigma functions as a by r square, and sigma theta functions as minus a by r square plus b. So like depending on the boundary condition, now that we have the solution, like this solution satisfies this Laplace equation that gradient square 4 of phi is equals to 0. So now we can basically write every boundary conditions and find the constant a and b. So like let us assume that there is a cylinder with a hole, and like there's a cylinder with a like there's a concentric annular cylinder with the hole. So like there are two radius r1 and r2. So like obviously r2 is greater than r1. There is a pressure p2 at r2 and there's a pressure p1 at r1. So we can define, basically we can just basically put these conditions inside this, and we have the sigma r and sigma theta boundary condition. So basically by putting this we find a and b. So in the end we basically have this condition that sigma r would be p2 minus p1 upon 1 minus epsilon square alpha square plus epsilon square p1 minus p2 upon 1 minus epsilon square. Well, alpha is basically r1 by r. So basically these two ratios will define that epsilon is equal to r1 by r2 and alpha is equal to r1 by r. So basically, like by putting in the values of a and b, we basically get these in terms of the pressure values which we basically calculated. So like this basically perfectly describes the state of stress in the cylinder. So like from this we can basically have a lot of special cases where like p2 is equal to 0. So like p2 is equal to 0, then in this equation you can just put p2 equals to 0. And then some cases are that r2 is infinite, so you can put r2 as infinity and like epsilon will go to 0. And so in this case you will have basically this kind of state of stress. So basically this is what the axis, the function looks like in polar coordinates, and like we can basically solve it very easily for axisymmetric problems in polar coordinates, and we have this generalized solution form. So based on any boundary conditions you can just basically find the sigma stress and strain function. Like the derivation for like how we found the solution for this is basically inside in the notes, and like you can look it up, but like I don't think so it's important as such for an exam perspective. You only have this function, so like you just only have to satisfy the boundary condition and find the stress function for exams, for any question asked in the exam. So like these are all the other cases, like you can just p1 equals to 0, then you can just put p1 equals to 0 in this general condition, general equation. So yes, this was basically everything we had on the stress and strain theory. And after this, there is a slightly advanced topic for this, like which you can read on additionally. But I don't think so it's important for an exam perspective. That is basically stress-free hole and uniform tension. It's basically given in the notes, but I don't think so it's any. It's an important concept to be learned. It's just basically the same as putting the boundary conditions for this function. So you can just check it out, and after this we can have the final topic of our discussion, that is beam theory. So see you in the next video.